So I'm going to talk about error correcting codes, or FEC, so called. It's used in almost everything, but not balloons, and so frankly it should be. If I say any terms that you're not familiar with, it's probably because I don't realise I'm saying them, so tell me. So why should we bother? Well, first starting to see that waterfall, that's sort of when you'll know the balloon's falling, it's moving around, and that's not going to the code, even though it's a pretty strong signal apart from the bits that are missing. But generally, we transmit 10 milliwatts of power. It doesn't sound like a lot, but we can still transmit less. When the balloon's very high, it's still very strong signal. So you either transmit less power, save power, or you can use it to increase throughput as well. So a bit of a history. So there's two main families of error correction code. The block code, which takes a large chunk of data and then tends to do a matrix operation to produce the parity bits. The parity bits being the bits we add on the end of our message, which are then used to do the error correction. And so there's you see what year they were developed in. This is quite commonly used in CDs and the old TV video standard. LDPC is a very high, very well-performing code. Was actually developed 63, quite a long time ago. Because at the time, the processing power to decode it was beyond them, so it got rediscovered in '96. And it's now used for the new TV standard, satellite standard. But even with the satellite standard, use it in conjunction with the Reed-Solomon, which might not perform well as well, but it's quite good for mopping up the errors, because that quite often produces an error floor, so every so often you get an error. So a low complexity code is used in conjunction. Convolutional code, which we'll go into more detail later, take in a bit stream and output a bit stream. And there's also some memory. And so the output bit stream depends on the memory states and the input. So a high complexity convolutional code is quite often used was used in deep space. That's the old algorithm, that's the newer one. And the turbo code combines two convolutional codes, and it uses the BTDR algorithm to the code. I'll go into more detail on that later. The turbo code and LDPC are both iterative, which gives them the massive performance over the other ones. So start off very basic to get the concepts. So a repetition code, you see we put a bit input, we then add our redundancy, transmit it, we get some noise, some bits are corrupted, and then we try. And then for this one, we just do a majority vote. And most of them corrected, but it's not very good, so one bit's still left in error. It's a third rate of code, so when I say rate of code, it's a third of the transmitted bits are the original signal. So it's saying how many parity bits are we adding and how much is the original data. So a third of what we transmit is the original data. We can improve it by using soft information. That is, after the modulator, instead of deciding if it's a 1 or a 0, we assign a probability. So we have we can assign a confidence in a bit, which you can see in my example now that we're correct in our decoding. And so if a bit is raised, you get some noise and a bit is sort of on the boundary, you can say we're not very confident, we're not going to assign much, what's the word I'm looking for? Anyway, you can see that in this example works better. We usually use the probabilities in the log domain because it makes numbers a lot easier, such that a positive number is a 1 and a negative number is a 0, and the 0 is we're not sure. Everything else there. So I'm not going to say much about this, don't really know much about it. But the two examples I'm going to use later on is a very bad one, and one that's used quite a lot. I think that's what SSDV uses. So in this example, this is a non-binary code, so it works on bytes. And so this one transmits 255 bytes with a message input 223, so there's 32 parity bytes. And by the way the RS code works, it means it can correct 16 byte errors and detect 32 byte errors. And so the way we judge the performance of these is a bit error rate plot. So we've got the SNR along the bottom, and then the probability of an error here. And so you can see the uncoded one is here, and it's, not surprisingly, the worst. And then the repetition code using soft information is that much better than the one using hard information. The RS code that doesn't send that much parity, if you look at it, it's a 0.87 rate code, so you get most of the message through, not sacrificing that much. That doesn't go so well compared to the one that sends a lot more. But obviously this isn't particularly fair because this one is using a lot less parity bits than that one. So this uses a lot less power to send a message than those other ones. And so you have to send the parity bits, so you either have to put them on at the end, so you're spending longer transmitting the same amount of power, so the energy you use to transmit a message is higher, or you can transmit the parity at the same time, in which case you've got to increase the transmit power such that the SNR stays the same. So you see both ways it's not fair. Which is why I don't tend to use SNR. We use EB over N naught, where EB is energy per bit and N naught is noise power spectral density. But essentially, EB over N naught is SNR per data bit, where you've got, for each data bit, you've got to take into account the parity bits you also have to send with it. And so to convert, there's this, which that's just the conversion to the log domain.
There's no count of bandwidth.
We obviously a higher rate code needs more bandwidth. On the SNR plot, we don't take into account bandwidth, but it takes into account it's fair for power. So if we're transmitting the parity bits at the same time or higher bit rate, the transmit power is the same, and you're taking the same amount of time. So it's fair in case of energy.
Yeah.
So the SNR will be lower. But you've got to remember that you are using more bandwidth. So for us at the moment, we have spare bandwidth, so it's not really an issue. And if you're using phase shift schemes, you can go up to BPSK to QPSK to QAM that way. But yes, you have to take into account extra bandwidth you're using. Yes? So you send a bit over the channel that has a particular power at the receiver, and then you also have the noise from whatever sources has a particular power. So it's a ratio between the received power of a bit compared to the noise. I've got to be careful because it's all very similar, but that takes into account the parity, the fact you've got to send more data, not data, but yeah, bits. And so I've got these side by side of SNR and EB over N naught. And so now the RS code that doesn't send that much parity is now the clear winner, because the others, all the amount of energy they use is now counted against them. And so the repetition code that uses soft information is now the same as the uncoded, because if you're just repeating the data, that's the same as just reducing the bandwidth, reducing the baud rate, so you're actually getting gain. And so that one's worse now. The one that uses hard information repetition code. And really bad RS code you probably wouldn't bother using.
So the noise power that the DNO would be greater because of the bandwidth the signal's taking?
It's noise power spectral density.
Right.
No. It's, yeah, I mean that's...
So it's not true. It's not a true comparison. I think that's the thing I'm getting to.
It's fair in case of transmit energy. It's not fair in case of bandwidth.
Well, I'm thinking more receive comparison.
Yeah.
Don't get too
Well, I can think of it. It's fair in case of energy. I was trying to think of an example, but yeah. So you're saying if you use more bandwidth with the same, but the
signal you need more bandwidth to get it through. When you receive it, you will be taking in more energy, more noise energy.
Yes. So the reason this does better because the decoding gain overcomes the fact that the SNR is worse if you were to to use more bandwidth, but the EB overrun nor Brejza. So I mean, it does work if you have. I always had to spend quite a lot of time on this stage because it does mess with your head a bit.
Yes. Well, that's definitely true.
But if you think it through, it does work because it's used all the time.
I'll take it.
Exercise for the students.
Yeah, if you sort of work through what's happening, and it does. Because if on the SNR scale, you can see these are much better, and so it does sort of work, I promise. So the turbo code, the one I'm drawn is the one that's used in LTE, so it's sort of state-of-the-art code. So these two highlighted boxes are convolutional codes. Yeah, pretty simple, really. That's just a memory element, so 1 bit at a time, send it through. That's an interleaver, so this is encoding essentially a completely different sequence of bits to that one. Then we send through the original uncoded data, they call that the systematic bits, and then 2 sets of parity bits. And so it's a third-rate code, but you can puncture it, which means you just don't send half the parity bits if you don't want to. So you get to the desired coding rate. The receiver, we have 2 BCJR decoders which match up to encoders. And if you follow it through, it's kind of the same, but we double up all the wires. So just to go quickly through how it works, this takes in data, encoded data from the channel, and also uncoded data from the channel. So these match up with, say, those two. And then it outputs its estimate, its best. It takes in the 2 inputs and thinks, what can I work out? So that's its estimate here. Now then we operate this one. This one also takes in data from the channel, the uncoded, the encoded, but then it also takes in data from this one. So this one will then output its best estimate, but that will be better than that because this one's got information from this one. So we feed that one through to here. And so we cycle through, each one adding a bit more information and passing it to the other. So that in the end, when we finally decide to produce our output, they add everything together and have got ourselves a hopefully a corrected message. This uses soft information because if you're wanting to pass confidence levels between the two, it's not going to work with ones and zeros. And so to see how well it works, first of all, just to see how good the iterative process actually works. So the uncoded is right at the top. Even after one iteration, we're pretty all right. So that's not really iterating because it's just one then the other. But then as we do more and more iterations, we get down to sort of brick wall almost performance. So that's with only 1,000 bits. These work better with more and more bits. If you were to go silly number of bits, it's a brick wall like that. That's SNR for some reason. And there is a theoretical limit here, so you can't operate in this region.
So like what it would be for an infinite number of iterations?
Infinite number of iterations. It would only be like there. It's not going to keep going.
It's still about 2.5 dB away from the channel.
Yeah. LTE can go up to 6,144 bits, which is on the next slide. And that's a bit nearer. And to the extent that when I was simulating these, you didn't really get any errors here because it ran it long enough. So that's showing that we can change the coding rate from 1/3 to say 0.9 and get the as worse as you would expect. The RS code doesn't do too badly actually in comparison, bearing in mind that's a lot less effort to the code. The uncode is quite bad, obviously. All this is in a white noise channel as well. And also it's BPSK, but ignore that. I'll get into different modulation schemes later. And then previously it was bit error rate. So a frame error rate or sentence or packet error rate might be more useful if you're thinking of you're sending sentences through. So I've gone for 1,000 bits, which is probably a longish sentence. And then we can see, if we want, say, a 1 in 100 probability of an error, we can see what power we need to transmit to, get decent low enough errors. So from there to there is about, I think, 8 dB. I'm too far close to see it. So that's the gain from using a third-rate turbo code. You need 8 dB less power. Or another way to look at it is your 8 dB gain you could then use to increase the bit rate so you can get more data through, depending on what you want to achieve.
8 dB is a bit
Yeah. So capacity I've touched on. This equation that some fellow came up with, Shannon, a while ago, predicted the theoretical limit of a channel. So I've plotted it on here, but if you were to do that, it would shoot off up here. But because I'm limiting it to BPSK, which sends 1 bit at a time, it's capped up. This is spectral efficiency, so it's saying in a fixed bandwidth. You can send up to 1 bit per second per hertz. For RTTY or FSK, it would be the same graph, but these numbers are just a bit worse. And also, that's about a half instead of 1. So this is just a different way to show what we've been showing before. So we've decided that we want a frame error rate of 1 in 100. And so we're saying what's the lowest SNR that each of these schemes can achieve that frame error rate. So for uncoded, you need a EBO below naught of about 10 dB. So we can see 1 point something for the best turbo code. And so the closer you are to this line, the better you are performing. I think that's what I wanted to say about that. So now, a white noise channel is really nice and everything, but it's not really, you're lucky if you get a white noise channel, really. So that's not going to get any decodes, to be honest. So I made a rather crude model which essentially just wipes out some of the bits every now and then. And so I just done all the tests again, but using that as the channel. And so the graphs look the same, but you'll notice the scale is completely different. So now, from there to the uncoded is about 22 dB gain over using an uncoded system. And I'll quickly skip to the capacity one. So again, this looks the same. However, you'll notice the repetition codes have now got an improvement because the errors aren't even across all bits. It will wipe some out. So what I've actually done for these is I've interleaved them. So the errors aren't in the block. They're sort of distributed amongst the received bits. But yeah, it's just everything's just been stretched, and the gain you get from a code is now a lot greater. So I've briefly mentioned modulation schemes. So I've been using this red line for the simulations, when this line here is FSK and it's used by RTTY. And so there's about 4 to 5 dB lost in using our 1-tone or 2-tone 1-bit FSK. But these other lines are what happens if you use multiple frequencies. And so this one is 2 bits at a time. So that's using 4 tones, and so that's quite a big gap, bearing in mind the extra bandwidth you use isn't actually that great. But then as you get 3, 4, 5 bits at a time, the amount of bandwidth you're using just gets silly, because the bandwidth goes up 2 to the power of m. Well, the throughput only goes up by m. In theory, m equals infinity should get to the Shannon limit, but that's just stupid, really. So you end up using a gigabit of bandwidth for, 1 symbol a second or something. And now a slide I stole, image. So this is just the capacity again, but now we're showing different modulation schemes. So these are all uncoded. And so the thing to take away is that when you have lots of SNR and you want to get lots of bandwidth, if you want bandwidth, you use these phase shift schemes. They're very bandwidth efficient, but not particularly energy efficient. However, the multiple frequency shift keying can approach capacity, but the bandwidth is so much, the spectral efficiency is that much lower. So m equals 4 is not a bad option. We're not using that much more bandwidth. M is the number of tones on this one, so sorry about that. Got a few dB gain there. I think that's everything about this slide. Yeah. And there's just a practical example of deep space usage. So apparently they started off using uncoded systems at the top there. Started using, I don't know what bi-orthogonal is, convolutional code, 7 being the number of memory elements. So as you go up to 15, we're pretty good compared to, say, a turbo code. But every time you increase memory elements, the decoding complexity doubles. So this turbo code might only use 3 memory elements compared to 15 for that one. But this still outperforms it. And so I was thinking of a new telemetry string because, yeah, coding does have quite a lot of potential to improve things. And so what you've seen is that depending on the condition, the amount of parity bits you need to get a decent throughput, to get a decent bit error rate varies. And so you probably want to have a scheme that uses different numbers of parity bits, and the coder knows what size these will be, and therefore, once it receives one block, it can try and decode. If it doesn't, it can look for another one. And then if it receives the start of the next packet, it knows to not bother. I think people want to discuss that later, what we could do with this. What's actually quite important is that the decoder knows the length, because the turbo code needs to interleave as part of its operation. So if you don't know the length, your interleaver immediately breaks. But if you keep the length the same between strings, it's not much of an issue. You could either send the length, you could work out the length by the distance between the two sync sequences, and, well, lots to do. So in conclusion, we can vary the coding rate depending on conditions to get the desired bit error rate for whatever condition you're operating in. You can either, the coding allows you to either use this power or to operate in lower SNR conditions if you're wanting to get right near the horizon, or if you're landing and you want to switch to a higher code rate so you can get the last data, or if it's on the ground also, things like that. It allows you higher throughput if you're in clear space, if you've got lots of signal strength to work with. And it massively improves the performance when it's really quite bad channel conditions. The encoder complexity is quite low if you wanted to implement it. The decoder isn't, but computers are quite good these days. Any questions? Yes?
What's actually feasible on, let's say, an Arduino base?
What, the encoder?
Yeah.
I mean, these are just XOR operations. That's just a memory, 1-bit memory. The interleaver you can generate on the fly quite easily. LTE, because if you've got LTE is quite high speed, say 300 megabits, you don't want to have this massive memory to store your interleaver addresses. You can generate it just using additions, your next interleaver address. So, not a lot.
Do you want to write a library?
It's not that much issue, but I'm sure people would appreciate it. Anything else? Yes?
You may have already answered this, so if you have, I apologise.
Okay.
But I'm just thinking back to, if you go back to sort of 80s, 90s, when people were just sending video conferencing, they couldn't get the bandwidth they needed down the phone line for it to work effectively.
Yeah.
And some guys did something which I thought was really clever, which is he said, actually, if you look at the general pitch that you're transmitting, there's only a small bit that's changing each time.
Yeah.
So just transmit the stuff that's changing.
Yeah, so that's video compression.
But,
so
but if I actually look at the majority of the strings that come down, quite a bit of that information is the same from, for example, you only go through, let's say, a couple of different sort of main longitude or latitude lines in a flight.
Yeah, so if you were to...
What's the potential to do something clever on the coding side to stop, or to at least...
well, what I didn't bother going into, it's not really the presentation, but if you were to do this, what you would probably do is you have multiple GPS positions in one string. So you start off by sending a GPS coordinate. You might send it in binary format, because ASCII's a bit, you waste quite a lot. So you send it in a binary format, and you can send 10 other GPS strings, but you send the difference. So you say, let's move that many each time. You then store, you say they're 1 second apart. So you can send 10 GPS positions, say they're 1 second apart, only use, say, a few bytes for each position, and to be honest, you can just send 10 hertz GPS positions down without using any more bandwidth. So there is a lot of potential if you wanted to do something here.
What have we seen in the way of improved beyond the edge of line of sight with things like Domino EX?
Well, I got it down to -1 degree elevation. So that was Domino EX. It gets its performance from being a multiple frequency shift key scheme. Also, the baud rate's very low because it doesn't use ASCII. There is some trellis code and modulation on it, but I don't know how much that adds. But it's mostly the reduced baud rate, the MFSK, which does it. So you could design 2 different formats. One is for getting decent throughput through, and one is a MFSK scheme that uses, say, maybe 8 tones.
I guess what I'm saying is, when you've got line of sight to a balloon, there's not a lot of problem receiving it anyway.
Yeah.
If you just want to get GPS data.
Mm.
If the aim is to get beyond the horizon, radio horizon, actually how much are we going to gain by using air-correcting codes? In other like, be able to get 300 kilometres beyond the horizon?
Well, I don't know what it is in terms of distance, because 1 degree horizon is probably considerably different to, say, 2 degrees below the horizon. I imagine it's quite a cliff in. If you were to draw the attenuation against degree at distance, it's going to presumably cliff off quite sharply. So I mean, without knowing how that affects
I
it.
reckon normally with over the horizon radar, that works to what, 4 over 3, so about the extra 30%.
Yeah. Radar, I don't know if it uses error correction coding, because you're not sending data, you're correlating 2 different signals against each other.
In terms of receiving a signal.
Yeah. I think the main advantage is if you're on the edge of just on the edge, or if the balloon's on the ground, or if you want to just send a lot more data through. Because now, the limit at the moment is maybe 600 baud. I don't think anyone's really got higher than that, but we can now fill the spectrum, add a bit of error correction coding, and be more reliable and get more data through. So I think that's where you would want
to... What's the data improvement, do you think?
I reckon you can fill the spectrum, the 3 kilohertz. Yeah. So if it's like an 8 to 9 dB gain, bearing in mind at the moment there's still quite a lot of dB headroom when we're in the air. You get maybe 15 dB gain, so whatever that is, and 10 times bandwidth easily without trying too hard. I think that would be a reasonable guess. Yeah, I think the issue there, we don't have the spectrum to do it. And no, although with the FunCube dongles, of course, you could use the entire spectrum with a MFSK scheme, error correction, and annoy everyone else.
Yeah,
goes over the top. Anyone else?
Can you potentially combine information received from several receivers?
I guess if your receiver is outputting LLRs, so probabilities, on the habitat servers, you could combine these LLRs. There's no reason why we can't at the moment. If one receiver gets a string quite well and one doesn't, and one gets another string quite well, you can't combine them. If you use soft information, it means that combining just works better. There's nothing we couldn't do at the moment, so it just will work better if you're using soft information. Anyone else? Yes?
Yeah, just to that, would it be clever to split it up in several packages? To just have parity packages and
Does this run out of battery? No. Well, so you're...
Because this way you can easier mix and match from different stations.
Well, as it is at the moment, the receiver will know. The receiver will start at this point here. I mean, it will know that's it. So it will know what position a bit is. So whether that's 1 packet or 10 packets, I don't really think it makes much difference.
Matt, in your channel
yeah,
pattern you had sort of
the fading one.
fading one.
Yeah.
Because I would say that's probably the more where we could gain a lot bit more information. That we go through a very wide range of being very strong, continuous, very little fading, to the other extreme where you're probably fluttering 2 or 3 hertz easily at times. So at the extreme. Is there any advantage in any other particular one by making the block longer? So that we can spread the data over?
Yeah, a longer block always works better.
Yeah.
So it's a case of 6,000 bits is quite a long message. You might want to send that. So I picked 1,000. I thought that'd be quite a good representative size. If you're sending more data through, then a longer block isn't so much of an issue.
Is there an optimum point though, where if we increase the fading rate, where we find there's an optimum between block length and data throughput?
Well, block length, if you increase the block length, it doesn't really change your throughput. It's
So even with fading rates that were sort of half a block.
what you're saying if that is half a block wide?
Yeah. I feel that just sort of gut feeling that says there ought to be a point where there's going to be an optimum, and then after that it's going to fall off on both sides, either in terms of efficiency or in terms of error rate.
I would imagine that the longer block will always work better. I think you just try to pick the longest block you can for the amount of data you intend to send through.
Right, shall we? Is that to be?
Anyone else?
I think maybe half of us have missed the rest of the catching up with this talk. Does anybody else have any more questions? You have to move on.
Brilliant. Answer questions later on.
Yeah.
Yeah.
Can we say thanks for coming?